For this section, we're going to be looking at outcome FM 30.3. By the end of this unit, you should be able to demonstrate understanding of set theory and its application. So for our first lesson, we're going to be doing 3.1, types of set and set notations. And by the end of this one and the next lesson, you should be able to create a graphic organizer such as a Venn diagram to display relationships within collected data or sets of numbers. And so just a bunch of terminology first. We have a set, which is a collection of distinguishable objects. So for example, we could say the set of whole numbers, W, which is 0, 1, 2, 3, so on and so forth. We could say the set of weekdays, which we could say with the letter A, and that's equal to Monday, Tuesday, Wednesday, Thursday, Friday. And just a note, when you're listing off the elements in your set, make sure you're using squiggly brackets on either end. So all sets are named with capital letters, and sets are defined using brackets, squiggly brackets. When I talk about an element, that's an object in the set. So an element of this W, this whole numbers, would be like 2. Or Friday is an element of the set, so the days of the week, or Wednesday is, Tuesday is, so on and so forth. When we're talking about set notation, we can say n for the number of, and then whatever set you're talking about. So capital letter A in this case is 5. So how we read that is the number of elements in set A is 5. So when we're talking about the number of, we're talking about each individual element. So like when we're talking about this set A, there's 1, 2, 3, 4, 5. If I talk about a universal set, that's a set of all the elements under consideration for a particular situation, also called the sample space. So, for example, the universal set of digits D of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And a digit is a single number. And so typically when you start off a problem, you do define what your universal set is. If we talk about a subset, so a subset is a set whose elements are belong to another set. So example, the set of even digits is E, which is 0, 2, 4, 6, 8, belongs to the universal sets of digits D. So just to go back a page, this was my universal set, so the numbers 0 to 9. And so within that, I have the 2, the 4, the 6, and the 8. So my even is a subset of D. Or I could say the sets of odd digits, 0, which is, or O, which is equal to 1, 3, 5, 7, and 9, also belongs to the universal sets of D. So I use set notation to show that is this long C. So I say E is a subset of D, or O is a subset of D. And so basically every element that's in E is also included in D. Every element that is in O is also in D. If we talk about complements, all the elements of the universal set that do not belong to a subset of it. So example, if I say my set is E, so the even numbers, which was 0, 2, 4, 6, 8, and I'm still using that original universal set they were talking about, the 0 through 9. So then the complement of it would be everything that is not in E. So the 1, the 3, the 5, the 7, and the 9. And so to use set notation to show that, we use E prime, so E with this little tick. And so E prime, or the complement of E is equal to 1, 3, 5, 7, and 9. If I talk about the empty set, an empty set is a set with no elements, so there's nothing in it. So if I say set X, which is a subset of D that contains the number 22. So recall that D is the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means it can't contain the number 22. So there's nothing in X. So either we use 2 squiggly brackets with nothing in to represent the empty set, or we use this 0 with a slash through it. And so both those show an empty set. If I talk about a disjoint set, so that's 2 or more sets having no elements in common. So examples from what we were talking before, we had the even numbers of 0, 2, 4, 6, 8, and the odd numbers of 1, 3, 5, 7, 9. Those are disjoint because there's nothing in E that matches with O. And then we can use a Venn diagram to show our subsets with a universal set. So we had the universal set D, which is the set of digits, the 0 to 9. So that's my universal set, so that'll be my box. And then I have the subset E with the numbers 0, 2, 4, 6, 8. And the subset O, which was 1, 3, 5, 7, and 9. And as you can see with this Venn diagram, there's nothing in E that matches with O, so I have no overlap with my circles. You can have a finite set. That's a set with containable number of elements. So the set of natural numbers less than 6, so 1, 2, 3, 4, and 5. If I have an infinite set, that's a set with infinite number of elements. So the set of natural numbers greater than 6, so 7, 8, 9, it keeps going and going and going, and there's no end to it. So infinite, there's no end. If I talk about something that's mutually exclusive, highlight this one. This one's important. Two or more events that cannot occur at the same time. So when rolling a six-sided dice, you roll either an odd number or an even number. So these two events cannot both occur at the same time, so they're considered mutually exclusive. And typically, if something is mutually exclusive, when you write it as a set, it's going to be a disjoint set, typically. So for an example, we're going to indicate the multiples of 5, 10, from 1 to 100 using set notation and represent the sets and subsets in a Venn diagram. So there's a couple different ways to write this. And so I'm going to start with the most basic, and then from there I will show you how to condense it a little bit so you don't have to write as much. So if I am doing the multiples of 5, so I'm going to say A, which is the multiples of 5. And so the really basic is just to list off the multiples of 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and then I would just keep listing off the multiples of 5 until I got to the end. That's kind of time consuming. Not terrible with only going up to 100, but if I was going up to 500 or something like that, it takes a while. So to condense this down so I don't have to write as much, I can say A is equal to, and then I'm going to define the variable that I'm working with, so F, and then I'm going to say what F is. So F is equal to 5 times X, so whatever X is. And then I'm going to say X can be anywhere between 1, so 1, and so the highest I can go is 100. So to get to 100, it'd be 5 times 20. So the highest X needs to go is 20. Because if I go past that, then I go past my top range here of 100. So I'm going to say X needs to be greater than 1, but less than 20. And what I'm going to say is X then can be or belong to the natural number. So I'm going to use N. So just a reminder, natural numbers are numbers 1, 2, 3, 4, 5, 6, 7. If I say whole numbers, it's your natural numbers including 0. If I say integers, that's your positive and negative numbers, but no decimal places. If I say rational, that's throwing in your decimal places, but that's decimals that either end or repeat. Irrational is including your numbers that have decimals that don't end or repeat, like pi. And then if I say real numbers, that is anything possible with our number system. So if I do B, same idea. If I wanted to, I could take the time and sit and list off my multiples of 10 now. So 10, 20, 30, 40, 50, so on and so forth. A bit time consuming, so to reduce this, I'm going to say B. Same idea is I'm going to define my variable, so I don't know, S. And then I'm going to say my S is equal to 10 times whatever my X is. And then I'm going to give my range of what X can be. So in this case, I'm going to say, well, it needs to be greater than 1, but less than. So the highest I can go from X is, so 10 times 10 would make 100. So the highest I can go is 10. And same idea, that's if X is any natural number. So basically, I'm including everything but my decimal places. And then I should include my universal set here. So what do these two actually belong to? So I use U, and typically we use U for a universal set. So my U is then, so I could list off the elements from 1 to 100. So 1, 2, 3, 4, 5, 6, so on and so forth. But again, time consuming. So to reduce that, for my U, I'm going to define my variable of X. And then this time, like I'm not timesing X by anything, so I just have to give my range. So that X is anything. So it's greater than 1, but less than or equal to 100. So I'm between 1 and 100. And that's for an X that is any natural number. And so just a note, is I got some extra things going here. The best way to do it is this way, and this way. If you have a long string of numbers. If it's a short string, you can just list each individual element. So then to finish this question, all I need to do is show this in a Venn diagram. So then I have a box for my universal set. And I can just say U because I've already defined what U is. And then one thing that should be happening here, or I'm hoping you will notice, is that because we're doing the multiples of 10, 10, 20, 30, 40, 50, so on and so forth, that's included in our set of multiples of 5, 10, 20, 30, 40, 50, so on and so forth. So what that means is my set of multiples of 10, so my B, is completely contained in, or the subset of my set A, which was the multiples of 5. And then that's all included in our universal set. So then outside A and B, you'd have things that aren't multiples of 5 and 10. So like 2, 3, 6, 7, so on and so forth. Now I have done that question. So I've represented it using set notation and done my Venn diagram.